This is the non-AP Calculus Spring Semester Review Worksheet 3. Number 1 and 2 involve Riemann sums. So trying to use rectangles to approximate the area of a region. So we want to use, for number 1, use middle rectangles to approximate the region between 2 and 27 using two subintervals. And these are all order pairs that lie on this graph, but we're not asked to find the exact area under the graph since we don't know the behavior between each of these points. But we're going to use these to help us find dimensions for rectangles that we want to use to approximate our area. So first off, we want to extend from 2 all the way to 27. So we're going to start at 2 and we're going to end at 27. And we want to be able to separate each region into the same number of subintervals. So 2 subintervals, and we want each subinterval to be able to view or to be able to span across the same number of order pairs. So if we kind of just count and just kind of do a little bit of trial here, if I go from 2 to 16, that's going to span across 1, 2, 3, 4, 5 order pairs, and the second subinterval is going to pick up where we left off, and make sure that you always overlap your subinterval ends. So we'll pick up at 16 and go to 27. So 1, 2, 3, 4, 5. So we know that both span across the same number of order pairs, even though these order pairs may not span, these dimensions may not span the same width, but we are going to use the same number of subintervals. So if we take the values, the x values, between the highest and lowest of each subinterval and subtract them, so 16 minus 2 is 14. So 14 will give us the width of the first subinterval. And for a rectangle, we also need height. So for height, we want to choose one of these y values. And the y value that we want to choose is the one that's in the middle, because we're asked for middle rectangles. So 2 is the height. 14 is the width for the first rectangle, so 14 times 2 will give us the area for the first rectangle. Okay. Second rectangle is 27 minus 16. That's a width of 11, or difference of 11, which is our width. And then the height that we want to choose is the 12, so 11 times 12, we get 14 times 2 plus 11 times 12. That totals up to be 160. So 160 is our approximated area for this region using two middle rectangles as identified by what they want us to do. Number 2, use trapezoidal sum to approximate the definite integral from 2 to 30 using two subintervals. So again, we want to use two subintervals, but now these two subintervals we want to use trapezoid area formula, which is width over 2 times height 1 plus height 2. Now the width, we're going to find the width the same way. We're going to extend our subintervals, make sure that each subinterval sees the same number of order pairs. So 1, 2, 3, 4, 5, that's 5 order pairs, and then 1, 2, 3, 4, 5, again 5 order pairs. We still subtract the width to find subtract our highest and lowest x values to find our width. 16 minus 2 is 14. So that's going to be the width of my first trapezoid. So that goes in the formula, 14 over 2. Now the heights that we want to choose 2 heights. And the heights that we want to choose are the ones at the end of each subinterval. So we want to choose the 6 and the 5, because those are at the endpoints of our y values, endpoints of our subintervals. So 14 over 2, that's the formula, width over 2, and then height 1 plus height 2, so 6 plus 5. Now the second interval also just happens to be 14, but these values do not have to be the same. It just so happens that 30 minus 16 also gives us 14. But like we saw with number 1, even though we span across the same number of order pairs, we're not guaranteed that we're getting the same width. But that is how we're going to draw them, to make sure that it does reach across the same number of order pairs. And now we choose the heights. For formula is second trapezoid is 14 over 2, and then the height is 5, because that's one endpoint, and the other endpoint is 10. So 5 plus 10, which is 15. And then we total those up together, We get 7 times 11 plus 7 times 15. We get 182. Okay, moving on to number 3. Find f prime. Before we want to find f prime, we see there's a whole mess under 6, so we want to rewrite it as parentheses raised to the 5 halves. And let's go ahead and push it up to the top and recognize that we're eventually going to go through chain rule. So with chain rule, we have to identify the outside portion and the inside portion and take turns with each of their derivatives separately. So the outside portion is the 6 parentheses to the negative 5 halves. We'll do power rule for this. And then separately, we'll take the derivative of those inside terms, cosine 3x and the negative natural log of 2x. So first up is the outside function. We do power rule, so multiply the negative 5 halves down in front, keep the parentheses, and then subtract 1 from the exponent. So negative 5 halves minus 2 over 2 is negative 7 over 2. So we took care of the outside's derivative. Now we're moving on to inside's derivative. So each of these we have separate rules for. Cosine becomes negative sine of u times u prime, and natural log of u becomes u prime over u. So cosine 3x becomes negative sine 3x times 3. And natural log of 2x, u prime over u, our u value is this 2x here. So the derivative of 2x is 2, so 2 over 2x. And then we just try to push this together here. We fill the parentheses with our original, what's inside the original parentheses. So this cleans up to be negative 30 over 2, which is negative 15. This parentheses gets dropped down to the denominator, and we fill that in with the cosine 3x minus natural log of 2x. And then this will stay in the numerator as negative 3 sine of 3x minus 1 over x. All right, number 4. Find the derivative for our natural log function. So if we want to find our derivative for natural log, we have to first expand. Or we want to take advantage of expansion properties so that our derivative will be less messy when we're ready for it. Okay, so we have an expansion property here. Natural log of a over b is equal to natural log of a minus natural log of b. So the natural log of the numerator minus natural log of the denominator. We can rewrite the denominator as 2 minus 3x to the 3 halves. We can push that 3 halves down in front. And now we're ready to apply u prime over u for our natural log rule. So the derivative for natural log of x becomes u prime over u, or in this case 1 over x. And then 2 minus 3x's derivative becomes negative 3 over 2 minus 3x. Okay, so we clean this up. We get 1 over x plus 9 over 2 parentheses 2 minus 3x after we multiply and combine some of these terms together. Okay, number 5, use implicit differentiation to find the derivative. We do have an expansion opportunity here. Natural log of x square root of y, we can think of this as natural log of a plus natural log of b. I can rewrite that square root of y as y to the 1/2. We can go ahead and pull that 1/2 down in front, and we have our expansion for each of these terms. We have to also involve implicit because we have a couple of y terms spread out across our problem. So when we come across each of these terms derivative, we're going to have to make sure we include our dy dx that attaches to these derivatives. Okay. Let's go through each of these terms here. Natural log of x becomes 1 over x. 1/2 natural log of y becomes 1/2 u prime over u, or 1 over y. We just took y's derivative, so we need to include that dy dx. E to the 6x becomes e to the 6x times 6. On the other side of the equation, 3e is a constant, so that constant will go to 0. 5y becomes 5. The y goes away, but we're asking for y's derivative, so we need a dy dx. And then 3x squared becomes minus 6x. Okay. We have our derivative, we just have to kind of rearrange it to get our dy dx terms by itself. So I'm going to make these two terms move together to the same side of the equation. So I'm going to add the 5 dy dx over. And then all the terms that do not have dy dx, I'm going to have them make their way to the other side of the equation. So I'm going to add the 6e to the 6x. I'll subtract the 1 over x over to the right side. We're almost there. Just have to factor out the dy dx. And then move the parentheses back down below the this numerator expression. And we have our slope formula, our derivative equation that will describe the steepness behavior of every point on this original graph, whatever this graph looks like.